So in this set of information, we're going to add a couple of different ways to prove that triangles are congruent. So far, you have SSS and SAS. Today we're going to add three more. One is called ASA, one is called AAS, and one is called HL. This one is a postulate, and these two are theorems. Along the way, we're going to get another theorem that's going to become important later on, but we're going to need it in order to prove the HL theorem. Okay, so let's start with the ASA postulate. Essentially, this says that if I have two triangles and I have this angle congruent to that one, this angle congruent to this one, and the included side, right? So two angles and the included side, then I can conclude that the triangles are congruent. Now, ASA requires the side to be included, much like SAS required the angle to be included by the two sides. Now, the question is, well, will this still hold if the side is not included? And in fact, it does, and that's what we call AAS. And we're going to prove that theorem in a moment here. Okay, so AAS theorem at its base level says that if I have two triangles and I have two angles congruent and the non-included side congruent, then I can conclude that the triangles themselves are congruent. Now, this is not as obvious as ASA, so this is going to require a little bit of proof. The proof's not too big, let's see. I'm going to start a new page and we'll get it on there. Okay, so let's prove the AAS theorem. So let's build two triangles. We'll call this one A, B, C, and the second triangle, we'll call this one D, E, F, and we'll build these in such a way that this side is congruent to that one, and B is going to be congruent to E, and C is going to be congruent to F. So this is what we're given, right? We're given triangle ABC and triangle DEF such that segment AB is congruent to segment DE, angle B is congruent to angle E, and angle C is congruent to angle F. And what we want to prove is that triangle ABC is congruent to triangle DEF. I want to show that we have sufficient evidence for that. So we have statements and we have reasons. Okay, so right off the bat, we're given a bunch of information here, so let's get some of that on the board. Angle B is congruent to angle E, and C is congruent to angle F. And how do we know this? We are given it. Okay, so that's pretty straightforward. Now, but we have two angles in one triangle congruent to two angles in another triangle, so the third angle, angle A, has to be congruent to angle D. So if two angles in one triangle are congruent to two angles in another, then third angles are congruent. Okay, so that's a mouthful, but that's pretty much what it says. So that's going to give me, we got that earlier, that's a direct result of the triangles having to add up to 180. So we now know that A is congruent to D. And here's the deal. That's an angle, that's an angle, that's an angle, that's an angle, and that's the included side. So I have the win. I have that triangle ABC must be congruent to triangle DEF by the ASA postulate. So we can use the ASA postulate to prove the AAS theorem. All right, so that gives us 4 methods at this point. No, yeah, 4 methods at this point to give triangles congruent, right? We have SSS, SAS, ASA, and AAS. The last one I'm going to give is HL, and that only pertains to right triangles. The H stands for hypotenuse, and the L stands for leg. But in order to do that, we have to know something about isosceles triangles first. Okay, so we're going to call, this is a named theorem, so it's going to be called the isosceles triangle theorem. Basically says that if I have a triangle that has 2 congruent sides, then the opposite angles have to be congruent. So if this side is congruent to this side, then that angle has to be congruent to that angle. All right, so the proof here is a little bit of work, but we'll get it, and then we'll move on. All right, so I'm going to build our drawing over here because I'm going to need some room. And we're going to start with an isosceles triangle, so we'll call this A, B, C. And we're going to know that this is congruent to that. So we're going to be given triangle ABC, where AB is congruent to AC. And we want to prove that angle B is congruent to angle C. And we'll have a set of statements and a set of reasons to try to justify this, right? All right, so the first move we're going to make is a little off the beaten path. We're actually going to bisect this angle A. So we're going to bisect angle A in such a way that the segment AD is the bisector, right? So we're going to say that, so we're going to construct segment AD such that segment AD bisects angle A and intersects segment BC at point D. And since it's going through A and it's going through D, I can say that that happens because 2 points determine a line. There's only one line that can do that, so that's pretty clear that that's the line. Okay, so from there, I now know that angle BAD has to be congruent to angle CAD, because we said that this is a bisector. So that's the definition of an angle bisector. Okay, so that's great. So I know these angles are congruent. I also know that segment AB is congruent to segment AC because that's part of the given of the problem. And finally, segment AD, the one that I just created, is in both the left triangle and the right triangle here. So segment AD has to be congruent to segment AD, and we say that that's because of the reflexive property, right? Because everything is congruent to itself. Okay, so if you look here, the left triangle here and the right triangle here, I have sides. I have another set of sides, and I have an angle in between them, which means the triangle BAD has to be congruent to the triangle CAD, and that's by SAS, right? That's by the SAS postulate, which is one of the 4 ways that I have to prove triangles already. So ultimately, I can say that angle B is congruent to angle C, because if these 2 triangles are congruent, then their parts have to be congruent. And if you remember from a video a little bit back, we said that there's an acronym for this, and it's that corresponding parts of congruent triangles are congruent, which is this CPCTC. So we've proven what we set out to. If opposite sides of a triangle are congruent, then the angles opposite those sides are also congruent. And we're going to use this to ultimately prove this HL theorem, which is a little bit of a lengthy proof, but we'll get there. Okay, so let's first state what the HL theorem says. Okay, it says that if I have two specifically right triangles, okay, so this doesn't work for any triangle other than a right triangle. If I have two specifically right triangles, and the hypotenuses of these triangles are congruent, and one leg of the triangle is congruent, hence hypotenuse leg, then the triangles must be congruent. Now, this looks like ASS or SSA, which we said doesn't work, so this is a special case of this. This only works if that angle is 90 degrees. Okay. Otherwise, we get the ambiguous case, and we're not having necessarily congruent triangles. But if they are right triangles, then this will work. Okay, the proof for this is rather quite lengthy. So I'm going to ask you to kind of bear with us on this a little bit, and we might have to go through multiple pages here, so hang in there. Okay, so here we've got two right triangles. Okay, so there's one, and here's the second one. And we're going to call this one A, B, C. We're going to call this one D, E, F. Okay, and we have that the hypotenuses are congruent, and we have that a leg are congruent. Okay, so that's our given, right? Given right triangle ABC and triangle DEF such that AC is congruent to DF and AB is congruent to DE. And we want to prove that triangle ABC is congruent to triangle DEF. Okay, so let's see how we do this. The first thing we need to do is we need to do a little bit of constructing. Okay, so much like the last proof, there's going to be some constructing going on. So we are going to construct a point G on the line EF so that G is well, let's try to write it this way, that the segment CB is going to be congruent to the segment EG. Okay, why can I do this? I can do this because of the ruler postulate, because I can measure the distance here, construct a point G here on this line. So it's going to be the point G, so that this distance is the same as that. So I can create the correct distance. Now, that's also going to allow me to put a little line here. We'll call that one DG. Okay, so that's kind of a bit of a tricky bit, but it's going to be able to give me the room I need to be able to solve this. All right, so I also know that triangle ABC and triangle DEF are right triangles, and I know that because that's given, so that's useful, right? So this means that angle ABC and angle DEF are right angles, and because that's what it means to be a right triangle, right? So that's the definition of a right triangle. It tells me that it has to have a right angle here and it has to have a right angle here. Okay, so that's important. This means that these two angles, the measure of angle ABC has to equal the measure of angle DEF, and they both have to equal 90 degrees. Okay, so that's the definition of a right angle, right? Okay, so not so bad there. All right, so that gets me partway there. But now I start working at some other things here. I get that the angle, these two angles here, right? The angle FED and the angle FED and the angle DEG, right, are going to have to add up to 180 degrees. So I get that the measure of angle, let's call it DEF, plus the measure of angle DEG have to equal 180. That's by the angle addition postulate. Okay. Well, a little bit of substitution here, right? Tells me that since DEF is here, I can make that a 90, right? So 90 plus the measure of angle DEG should equal 180, because DEF is equal to 90, so that's substitution. Okay, so that helps. All right, so I'm out of room, so I'm going to have to clear some space here. Okay, so that gives me a little more space to work with. So just to kind of carry something over from the last screen, I now have that 90 plus the measure of angle DEG was 180, right? So I just got that by substitution, right? So if I subtract 90 from both sides, I have the measure of angle DEG equals to 90, so that's subtraction. Right, we just subtracted 90 from both sides of that equation, which gives me DEG being 90, but earlier I said that ABC is 90, so that will tell me that the measure of angle ABC and DEG have to be the same size. So that tells me that angle ABC is congruent to angle DEG. Okay, so if they're both equal to 90, they have to be congruent to each other. That's the definition of congruent angles, right? Two angles that both have the same measure. They both have the measure of 90. Okay, so that gets me an angle in this triangle congruent to an angle in this triangle. This side is congruent to that side, right? But we're also given that AB is congruent to DE, right? So that's here in the givens. So that's in the given. And now I have a side, an angle, and a side in two triangles. So that tells me that triangle ABC is congruent to triangle DEG. And how do I know that? By SAS postulate. Okay, so why did I do that? Okay, so the key here is that I now have that these two triangles are congruent, and if you look, well, segment AC is in the triangle on the left, right? I'm actually going to put this in the right order. Segment AC is in the triangle on the left, and this one, DG, is in this triangle over there. which means these two things have to be congruent because they're corresponding parts of these two triangles. So if they're corresponding parts of congruent triangles, they must be congruent. So that's that CPCTC bit. Okay, so here we go. We're going to need another page yet. So let's clear some. Okay, so a long proof this one is. All right, so, but we can do it. So we're back to statements and reasons again here. We're given, we just got that DG is congruent to AC, and we got that by CPCTC. And if I look, I also know that AC is congruent to DF because that's in my givens, right? AC has to be congruent to DF. Right? AC is congruent to DF, that's in my givens. So I have AC congruent to DF, that's given. Okay. So what do we got here? We have DG congruent to AC, AC congruent to DF, which means that DG is congruent to DF. That's the transitive property, right? All right, so if A is congruent to B and B is congruent to C, then A is congruent to C. That's the transitive property. Okay, so now DG and DF, that means that angle F has to be congruent to angle G. Why? Because this is an isosceles triangle, which means that's congruent to that. Okay, so that is isosceles triangle theorem. That's why we needed that theorem from before. Okay, so that works. All right, so what else do we know? We know that this triangle is congruent to that one. So that means G is congruent to A. Sorry, G is congruent to not A, but C, right? Because these two triangles we proved congruent before, which means that's by CPCTC, right? Okay, so what does that give me? G and C are congruent. Well, if G is congruent to C, and we know that F is congruent to G, that means angle F has to be congruent to angle C. That's again the transitive property. Okay, so and here's the big finale. Because if I start kind of looking here, I now have C congruent to F. I know that AC is congruent to DF because that's in my givens. I have AB congruent to DE. That's in my givens, right? Let me back that up a second. The last thing is not as important. It's actually that these two are congruent because of the givens. These two are congruent because of all the work I just did. And this and this are right angles, which means that's in my givens. These are right triangles, right? So those have to be congruent. That gives me two angles and a non-inclusive side. Two angles and a non-conclusive side tells me that triangle ABC has to be congruent to triangle DEF by angle, angle, side, AAS theorem, which is what we proved at the beginning of this video. So we had to use both theorems that we've already proven to make this one work. We've used the isosceles triangle theorem and we used the angle, angle, side theorem. Whew, that's a long proof. But it gets us there, and now we have 5 ways to prove triangles congruent in our system here. Okay, so we have 5 ways of proving triangles in our system. SSS, SAS, ASA, AAS, and HL, right? So SSS is all 3 sides are congruent. SAS is 2 sides are congruent and the included angle. ASA is two angles work with the included side. AAS is two angles work with a non-included side, and HL only works in the case where we have right triangles and you have a hypotenuse and a leg being congruent. Okay, so in the end, big notes here: ASS, SSA, and AAA. AAA. All no-goes. None of those will actually prove triangles congruent. Okay, so these are 5 that do, those are 3 that don't, and we will be applying these in days to come.